A viewer asked the right follow-up after the Flutter and Rust FFI video: if the native bridge matters this much, what happens when the native lane is Zig instead of Rust? The reason this needed a V2 is that the first answer was too narrow. One benchmark shape can tell you that native code helps, but it cannot tell you when the bridge itself starts to matter or whether Zig closes the gap once the workload changes. So this version is still a direct Dart FFI benchmark, not a full Flutter app benchmark and not a package shootout, but it is more serious about the question. Instead of one workload density, it sweeps three scenarios: boundary heavy, balanced, and compute heavy. The benchmark repo is intentionally small because I wanted the claim to stay auditable. One Dart harness drives the same seeded uint32 list data through three lanes: one Rust cdlib, one Zig cdlib, and one pure Dart baseline. Then the run writes the artifact trail. The fairness contract stays strict: same dataset sizes, same chunk size, same checksum gate, same Dart side copy in and copy out behavior, same warm-up policy, same measured runs. Only two things change: which native library owns the hot loop and how many transform rounds each scenario performs. That distinction matters because boundary heavy is really a test of the toll booth. Balanced is where the copy cost and the native loop start to share the story. Compute heavy is where the math behind the boundary gets the loudest vote. Start with the boundary heavy 1 MB case, because this is where a lot of people expect Zig to shine. Rust averages 0.72 milliseconds, Zig averages 1.01, and pure Dart averages 3.78. So even when the compute density is low, Zig still beats pure Dart by a lot, but Rust keeps about a 29% lead over Zig. Move to the balanced case and the ordering does not just survive, it gets harder to explain away. Rust lands at 2.27 milliseconds, Zig at 3.60, and pure Dart at 13.35. Zig is now roughly 3.7 times faster than pure Dart, while Rust extends the lead over Zig to about 37%. Then the compute-heavy case tells us whether Zig eventually catches up when the native loop dominates. It does not. Rust posts 6.63 milliseconds, Zig posts 10.31, and pure Dart lands at 38.02. So even when the work behind the boundary gets much denser, Rust still owns the fastest lane in this implementation. I also care about stability because one clean screenshot is not evidence. Across 7 measured runs per case, Rust stays tight, Zig stays tight, and pure Dart stays predictably slower. The coefficient of variation is low enough that we are not looking at one lucky pass or one broken sample. If you scale by scenario density instead of by language fandom, the pattern is pretty blunt. Rust wins the boundary-heavy case, the balance case, and the compute-heavy case. Zig stays second in every one of them. Pure Dart stays third in every one of them. If you scale by dataset size, the pattern is just as stubborn. At 256 kilobytes, 1 megabyte, and 4 megabytes, the order never flips. In the compute-heavy 4 megabyte case, Rust lands at 28.12 milliseconds, Zig at 40.92, and pure Dart at 148.99. The speed-up view makes the middle option easier to understand. Zig is not losing to pure Dart here. Zig is beating pure Dart by about 3.7 to 4 times, depending on the scenario. That means Flutter plus Zig is a real acceleration path, just not the top lane in this benchmark. Memory is the weaker and more honest part of the story. Peak RSS stays in roughly the same band for the native lanes, and even the pure Dart lane is not separated by some dramatic memory cliff. So if you want the headline from this rerun, it is not about footprint, it is about wall time and throughput. The code explains why the result stays narrow. Dart still pays the same boundary cost before native work starts. The benchmark copies the chunk into native memory, runs the transform, and copies the bytes back out. That means Rust and Zig are competing on the same bridge, not on two different integration stories. And once the bytes do cross that bridge, the hot loop is where the languages separate. Both native lanes pull far ahead of pure Dart, but Rust stays ahead of Zig in every scenario we measured. That does not prove Rust is universally better than Zig. It proves that this Rust implementation is consistently faster on this specific FFI workload. So where does Zig still make sense? If you care about Zig's C interop model, its language style, or a simpler path into existing C-shaped ecosystems, the benchmark does not invalidate that choice. It says Zig is a legitimate native option for Flutter when you need more speed than pure Dart gives you. Where should you still keep work in Dart? Keep it in Dart when the hot path is not actually hot, when state movement is more expensive than the math, or when integration simplicity matters more than squeezing out the last multiple of throughput. The boundary is real, even if it is not fatal. The practical verdict is narrower and more useful than a tribal language take. Use native FFI only when the compute win clearly pays for the hop. If you want the fastest lane from this benchmark, pick Rust. If you want Zig, treat it as a real second-place native option that still crushes pure Dart, not as an automatic Rust killer.